Okay, guys. I just this morning I uploaded the assignment, the wiki assignments for section C and D. We're gonna cover them together, and we're starting with that today. So take a look. I set the due date for a week from today. So hoping that from Thursday next week to Saturday, I can work and polish that list so that you have all the solutions, and then um, you can prepare for the exam, which is on March 2nd. So you'll have we should be able to have everything ready by the beginning of the weekend. All those wikis. Hopefully, as you start, I keep editing, and it's always a work in progress. But I want it to be finalized by Friday, so that you have it for the weekend before the exam. All right.
Question.
Mhm.
I still haven't seen that example or whatever you mentioned to me last class on Tuesday about my B32 problem.
Oh, sorry, Sean. I forgot about that. I'm so sorry. I'll do that. Let me let me write it here.
I could
One
email
second.
you if you need a reminder, but since its due date is close to February 20th, now I don't have much time.
Yeah, okay. Yeah, no problem. I'll do that this evening. Okay, this afternoon, as soon as I finish with my school work. So I already
Okay.
have I
Good
already
news is
have it
at least I
configured.
evaluate each answer. It's just I need to submit it in the way you would
Yeah.
want me to.
Yes, thank you for reminding me. I forgot about it, but I'll do it today. Okay, I'll do it today. I have my post-it right here now.
Okay, thank
Okay,
you.
okay. So let me tell you what these two sections are about. We're gonna do we're gonna count what are called distributions and partitions. And I'll tell you, I'll give you like an example of a problem and its variations so that you can distinguish what each is. So it's similar to, permutations versus combinations. So what are we doing here? Um, so we're going to do distributions and partitions together. And remember, it's not so much about the name, but rather understanding what we're counting. Okay. So I'm going to consider problems where you have just to set ideas, and this goes in regards to the next class activity that we'll have. Imagine that you have balls and boxes. You want to distribute some balls into boxes, and sometimes the balls are all different, or maybe they are completely identical, and the same for the boxes. Okay, so what you need to have in mind is number of ways to distribute or to place balls into boxes. Um, or you can also think people into classrooms. Or maybe let me not just add that as an example here, because people are already different, and here balls into boxes, balls are sometimes different. The set of balls that you have are sometimes different, sometimes identical. So let me write here, maybe we'll make a table, all the different situations. Let's say, just to fix ideas, that you want to answer a question like this: in how many ways in how many ways can 10 balls, and here they could be different or identical, can be placed or distributed. Um, let's say into 3 boxes. And again, these boxes can be different or identical. So you have have a picture like this in mind. You want to put the balls into the boxes, but sometimes the balls are maybe all different colors, or sometimes you have some balls that half of the balls are blue, the other ones are red, or the boxes can be identical or the boxes are labeled. And so, for example, the one example could be people into rooms. So in that case, people are considered different and rooms are considered different. Or people into groups, not necessarily rooms, just forming 3 groups of people, 3 groups of 10 people. Uh-huh. So that would be 10 people are all different, and you're just making 3 groups that are not necessarily labeled or anything. So the boxes will be the same. So let me write, as examples. So that you can fit into this problem, right? So in how many ways can 10 people be assigned or yeah, be separated into 3 groups? Mhm. So in this case, you can think of the, people assign it to different balls, to fit it into the general problem. So I'm going to say this is my general problem or problems, because you have variations depending on whether you use different or identical. And you have the groups as identical boxes. Mhm. Or you can have the same problem. Like I'm not telling you how to solve it yet. Just the type of problems that you can fit into my general type of problem. So in how many ways can 10 people be placed into 3 rooms? So maybe I could specify that the rooms are different. Maybe I don't. Maybe we just assume, yeah, they're different rooms. And so in this case, you can say, you can associate people to having different balls in our general problem, and the rooms being also different boxes. Hmm. Or maybe you can talk about, um, so I have different, yeah, or you can talk about in how many ways can, um, 10 identical t-shirts be placed into, and maybe I should say here different, but maybe from the context you can infer that these are different drawers, you know so the drawers typically, maybe you have your drawers like this, so it makes a difference whether you use the top one, the middle one, or the bottom one, so that makes them different. But if the t-shirt side are identical, then you can think of the t-shirts being the identical balls, and the drawers being different boxes. Yeah, even if I don't add the room, the explicitly add the word different, then we assume from the context that the drawers are placed in a certain order or something. Mm-hmm. But in doubt, you can always ask, right? So these are just examples. Let's see, can I come up with one that, so I have different, identical, different, different, identical, different. So I'm missing something like an identical, identical, right? So maybe I can say in how many
10 clones.
ways. Yeah, exactly. So if you have clones going into rooms, right? And you will have identical into different, or groups of clones that will be identical into identical. Oh, let's do that. So in how many ways can 10 clones be separated into 3 groups, right? So that would be identical into identical. Identical balls into identical boxes. Now, if the groups are supposed to be doing different things, like the group for this group is going to play basketball and this group is going to play baseball and this group is going to play football, then the boxes are different. Yeah, so it depends on the context, but it's important to try and fit your problems to the different case scenarios. Okay, and there's one more thing that can vary that we're interested in, which is, are we allowing empty boxes? Like, for example, that it's necessarily not very clear if we say into 3 groups. Are we allowed to have an empty group, or does it really have to be 3 groups, right? So, that in this case, we really want to have 3 groups, but again, in doubt, you can always ask. But the other variation is, um, are boxes uh, allowing or not empty boxes? That's the other variation to the problem, right? So we can have different or identical boxes, and we can also add as a restriction that all the boxes are used, or not. So we have all those types of problems. So, and that's another combinatorial problem. I can ask you, how many different problems we have here in this general setting, right? So we have 2 possibilities for balls being different or identical, 2 for boxes being identical or different, and 2 possibilities in whether we allow or not to have empty boxes. So we have 8 problems altogether. And we want to understand that is like the standard problem set, but we should be able to adjust them, okay? So uh, let's see. So now I'm going to go kind of to the table that includes those 8 types of problems, all right? And this is just for 10 and 3, but we can generalize them. So let's say that I have, okay, so I'm going to have 2 columns for no empty box, one for no empty boxes. And the other one, I'm going to say empty boxes allowed. So that's the 2 variations. And then I'm going to say 10 different balls into 3 different boxes. So I'm going to label the balls, right? So 1, 2, 3, all the way to 10, and they go into the different boxes first. So 3 different boxes. So I'm also going to label my boxes A, B, and C. Yeah. So it could be different balls of all different colors into boxes labeled to keep to give away trash, whatever, 3 label boxes. Mhm. And another possibility is it 10 identical? So this time they're not labeled and they go into still 3 different boxes. Oh. So I'm gonna label the boxes. And I guess let's get started with those. I still have, hopefully things will fit. Ah, so, oh, okay. So there's one, there is another, and I'm missing 2 more. I'm missing when the boxes are identical. Oh my goodness. Don't fail me. Yeah, it doesn't matter. So here I'm missing one more, and then, oh, okay. I didn't need to be that precise, but I wanted it to be understandable. Okay. So here's my table, right? Oh, I need one more here. Around there. Okay. So I'm gonna have my 8 different cases, right? Here I'm missing 10 different, let's do identical into identical. And then we're missing, identical into, no, different into identical. So label into identical. Okay, so let's see. Many of these we already know how to count. So, and for others, we will have to adjust something or do some extra work. Okay, so here we go. Let's start with the first one. Let's start with this one. Huh? So 10 different balls into different boxes. So the trick here is answer the question where, or think of the question where the balls go. Mm-hmm. So you can think here. We can simply use the, it's a creative solution, I guess, but we can use the fundamental counting principle. So you can think of having the balls labeling my spaces, my spots, right? So 1 through 10. And then where the balls go, they can go into A, they can go into B, and they can go into C, right? So they have 3 possibilities. 3 possibilities, 3 possibilities. So each of these is representing going into A, B, or C. Make sense? So the tricky part here is to think about the problem this way. Just answer the question where the balls go. So ball 1, 3 possibilities, A, B, or C. Ball 2, 3 possibilities, A, B, or C, and so on. So this will be 3 to the 10. And just so that we can compare, I actually have the exact number. So this is 59,049. So the important thing, 3 to the 10, but just so that we can compare to the other 7 cases. Which one gives me more and how much more possibilities. Okay. I think the next one that's easier is this one. So we have identical balls into different boxes. Mm-hmm. And here the question could be, because the balls are identical, I just need to know how many in each box, right? So the key question, let's say, it's how many balls per box. So that's the question you need to have in mind. So I just need to know how many. And you can think about this as combinations with repetition or, solving. This is what we were doing before. Solving the equation, how many balls in A, how many balls in B, how many balls in C, and this needs to add up to 10. And because we're allowing empty boxes, that means that each one of these is greater than or equal to 0, which is the general setting for those equations, right? So the answer here is 10 plus 2 separators, or if you want the 3 minus 1, so the 3 shows up. Those are the separators. Choose 10 or choose 2, whatever you want. So this is 10, 12. 12, choose 10.
So how does the -1 work again?
It's the separators, remember? This is the number of pluses, the number of plus signs.
Yeah, just how come you wrote it as 3 minus 1 and not just 2?
Oh, I could write it as 2, but this is the number of variables or the number of boxes minus, right? So the separators are kind of separating my boxes.
Okay.
Right? I have 3 boxes. That's why I wrote it like that. But of course, you can write it as 10 plus 2. But when when I generalize, when I change this into M and this into N, then I want to, or K or whatever, I want to be able to write it in those variables. Mm-hmm.
Okay, thank you.
Yeah. So this one is the same as 12 choose 2, which is only 66. Just in comparison to the other one. Okay. So I guess the next one that I like to see is this one over here. So identical balls into identical boxes. You see, for that one, I just need to know how many per box, but it doesn't matter in which box they go, right? So I just need to know in how many ways can I write 10 as a sum of 3 numbers. Or how many ways to write 10 as a sum of 3 non-negative. Oh, actually positive, because this is wait, because I'm doing no empty boxes, right? So I need to have at least 1 ball per box. So a sum of 3 positive integers. So I just need to know how many per box. Same as in this other part. I need to know how many per box. So I just need to say 2 here, 3 here, 7 there. But 2, 3, 7 is the same as 3 to 7, any order, right? Because the boxes are the same. So this, this is, I can count them by hand, right? In fact, for this one, we're not going to have a formula, at least not for a very long time. This is actually, in general, pretty difficult. It's a number theory problem. So, but this is, in how many ways can we write 10? For small numbers, we can do it by hand as a sum of 3 positive integers. Well, We can have 1 plus 1 plus 8. And this one, by the way, counts the same as 8 plus 1 plus 1, any order, because the boxes are not labeled. So that counts as 1. All different orders of 1, 1, 8 counts as 1. And we can also have 1 plus 2 plus 7, 1 plus 3 plus 6, 1 plus 4 plus 5. And that's it for using 1, 1. And then I can have 2 plus 2 plus 6, 2 plus 3 plus 5, 2 plus 4 plus 4, and then 3 plus 3, 3 plus 3 plus 4. And that's it, I think. Do you see any other? See? These are the ones that use a 1, right? And so I need to add up to 9. 1 plus 8, 2 plus 7, 3 plus 6, 4 plus 5.
Shouldn't the last one be 3 plus 3 plus 1? Not 4.
We need to add up to 10, right? 10.
Yeah, 3 plus 3 is 9, plus 4 is 13.
3 plus 3 is 6.
Oh,
6.
yeah, it's early.
Yeah. Oh,
It's
that
early
happens
for
to
me.
me all the time.
Sorry about that.
Yeah. Yeah. So please tell me, because many times, I don't know, I'm sure you've heard the joke that mathematicians think how is it? I'm going to even say it in the wrong order, but think one thing, say another, write another. I don't know, whatever. That's me. So if something doesn't make sense, please let me know. So, you can count these. For small numbers, you can count them by hand in an organized way. So these are called, by the way, numerical partitions.
Question. What
And
did
these are
you
actually
write under each x variable, xa, xb, xc? I can't see those
greater than or equal to 0. Greater than or equal to 0. Because we're allowing empty boxes, then greater than or equal to 0. And then I'll write the other one very soon. So my answer in this one, maybe I should, maybe that was 3 choose 10. This one. And this one, I don't have a formula. Like, we just kind of did it by hand. But these are called numerical partitions, and there is a notation for it. This is partitions of 10 into 3 parts. That's the notation. And in our case, that was 1, 2, 3, 4, 8, right? So this is the number of partitions of 10 into 3 parts. And we don't have a formula. We did it by hand.
Do we not include 0?
We don't add zeros in this part because it says no empty boxes, right? So here we don't add zeros. Here we can add zeros. But if we add zeros, we can have 1 0 or 2 zeros, and that's it, right? And if we add 1 0, we're really looking at the partitions into 2 parts, right? So one part is empty, so into 2 parts. And if we have 2 zeros, it will be 1 part. So that brings to the, that tells us that this one implies this one. So if we actually allow empty boxes, it will be partitions of 10 into 3 parts, plus partitions of 10 into 2 parts, plus partitions of 10 in 1 part. Right, so that would be like having 2 zeros, this is using all 3 boxes, using only 2, using only 1. This is using all 3 boxes, which goes with the no empty boxes, right? So, so we already counted the ones for 3. So this is 8, right? And for the ones for 2, we have 1 plus 9, 1 plus 8, 2 plus 8, 2 plus 8, 3 plus 7, 4 plus 6, and 5 plus 5. So this is the 5. These are 5, so that's 5. And into one part is just this one, just one. So the answer here is 8 plus 5, 13, 14. So it's 14, but maybe I should have done this in blue because, that kind of comes from the definition that we had on the other side, that P partitions of 10 into 3 parts. So we don't really have a formula, but we have notation for it. Yeah?
Oh, so.
But at this point,
I just want to make sure for this part, how did you find all the possible ways? Or I'm guessing we're not allowed to use the same number twice or like flip them around like 8 in front and then followed by a +1, for example?
Yeah. So in other words, the 2 plus 8 counts the same as the 8 plus 2, right? So this one here, this counts as only one. All the rearrangements count as the same because think about it, in context, it doesn't matter if I have 0, 2, and 8, or 2, 8, and 0. These boxes are identical, so you just need to know how many balls into the boxes, but it doesn't matter if it's 2, 8, 0 or 8, 2, 0 or any permutation. So, and that's the definition of a partition. So in a partition of the number 10, you just care about what the numbers are, not in which order you write them. So 118, 181, 811, they all count the same, just is one partition.
Does P 10,3 change since we're doing empty boxes are allowed now?
Oh, the definition is the same. So here we're counting, we're using 3 boxes, using 3 of the boxes. So using all of them, using only 2, so 1 is empty. And this is using only 1. So 2 are empty. Make sense? Or I should probably have written, no empty boxes. Let me write like that. Sorry, guys. I think it sounds better. And since this is like kind of my summary table, maybe I should do that. So no empty boxes, which was the answer on the right. And this is 1 empty box. And this is 2 empty boxes. But the definition of the P, P10 means partitions of 10 into 1 part, which is just the number 10, right? And P10(2) means partitions of 10 into 2 parts. They need to be positive integers. So these are all of them. And this P10(3) is exactly the same as this one. They're counting the same. So this actually represents when there is no empty boxes, it will be 8, as we counted here. Yep. Okay, so let's see. This one. Let's see. The setting looks pretty much like the one on the left, but now, the one that allows empty boxes. So for instance, here, if A is 0, then that means that A is empty. So we're allowing empty boxes. So the only difference with not allowing empty boxes is that now each of the x's is greater than or equal to 1. It has to be positive, right? So this is kind of, so answering the same question, how many balls in each box? We have the same equation, xa plus xb plus xc equals 10, but this time around, these are greater than or equal to 1 because there are no empty boxes. I need to have at least 1 ball per box. And we know how to solve that. We do 10 minus the sum of these restrictions, 1 plus 1 plus 1. So I'm going to write it like that. Plus the number of separators, which is 3 minus 1. So the number of boxes minus 1. Choose either one, either this 10 minus 3, so 7, or this 3 minus 1, whichever you prefer. So let me just do 3 minus 1 because it's a little easier. So this one would be 7 plus 2, choose 2, or 7 plus 2, choose 7, plus 9, choose 2. This is 36. So maybe I'm going to box this one. Because that when I generalize it, then I'll know exactly what to do. This is the number of boxes. These are the restrictions. In fact, maybe I should have written 3. Oh, I know what I'll do. Give me 1 second. I'm gonna add something here. So I'm gonna add one more here. Maybe that's the one that I want to keep for the particular case. So 10 minus 3 minus 3 minus 1. Plus. Choose 3 minus 1 or 10 minus 3, whatever you want. So, so maybe that's the one that I want to box. This one right here. Because now you can see that's the number of balls minus the number of boxes. That's taking care of this being positive. And then this is the number of boxes minus 1. That's the plus signs. Those are the separators. And I can choose 3 minus 1 or 10 minus 3, whatever you want here. Okay. Questions so far? We're missing the 3 that are a little harder.
Can you explain the 10 identical, 3 different with empty boxes one more time? Just like real quick.
These ones?
Yes.
This ones, okay. So you see the difference here. Empty boxes allow, this XA is the number of balls in box A. Maybe I can write that for clarification. So XA, and the same for the others, right? Number of balls to go in box A, right? So because in this case, I'm allowing empty boxes, then the X could be 0. And that's why I'm writing this is greater than or equal to 0 here.
Yeah, I get the greater than and equal to. I think I'm just confused about where I'm thinking identical, but I'm thinking numbers and they're not identical.
Okay, so let's see. If the difference between these two is just that whether or not you can have empty boxes. So, for example, having all the balls into box A should be counted here, but it shouldn't be counted there.
Yeah, I get the difference between the two. I just don't think I understand how you got it in the first place, like the x plus x equals 10.
I see. So how I get these equations from the problem? Is that it or no? Or how?
Yes,
let me ask you something. So is it the first part of how I got this equation from the problem, or is it the second part of how I got this number of solutions of that equation?
It's just the first part.
So is it the first part? Oh, okay. So, I want to count how many of this is equivalent to solving this equation, because if I give you a solution to this equation, for example, let me write it over here. So let me write it over here, okay? So if I give you a solution to that equation, so XA plus XB plus XC equals 10. I give you a solution. One solution could be, let's say 3 plus 0 plus 7. That's one solution, right? So that's xa equals 3, xb equals 0, and xc equals 7. That's one solution. And that goes with having, you have 10 balls, and this is box A, this is box B, this is box A, this is box B, and this is box C. This solution goes with having 3 of the balls here and 7 here, and nothing in B. Now,
Yeah,
this is
I'm
where
just
we're
struggling
counting.
because 3, 0, and 7 are not identical, but we're saying we have 10 identical balls.
Oh, what's identical are the balls, right? So the balls are identical here. So I just need to know how many. I don't need to say, yeah. Good. Thank you for insisting. Yes, yeah. So, I don't need to say the green ball goes to A, to B, or to C, because there is no green ball. All of them are the same, right? So I just need to say how many to C, as opposed to the first row of my table. In the first row of my table, I actually have to say, okay, the green ball goes into A, the green ball goes into B, and so on. That's what makes these two different. And that's why I have this many choices here. This is a lot larger than this one, because in this one I just say, okay, just take 10 of them and put them there. In this other one, I have to say, okay, the blue one goes to Johnny, the green one goes to Anne. I have to be specific about which color goes where. Yeah. So here I have many more choices.
Okay, good. Thank you.
Good. So let's see this one. Let's see this one, and then these two. So this one is actually a little bit harder. When you don't allow empty boxes, it's harder. Now, you see here, the way I counted, you can think of strings of A, B's, and C's. If I have the string, so strings of A's, B's, and C's. Yeah, so of length 10. Mm-hmm. And the association is so maybe I'll do this. So for that one, the association is, if you have an A, B, B, A, B, C, C, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let's say. If I have a string like that, that's what I'm counting, then it means that ball, because this is order, so this is ball 1, ball 2, ball 3, 4, 5, all the way to 10. Mm-hmm. So it means that in box 1, in box A, box A, box B, and box C, A gets 1, 2, 5. So balls 1, 2, and 5 go in here. B gets 3, 4, and 6. And C gets 7, 8, 9, 10. Mm-hmm. So a string like that gives me this. But in the strings, I'm also allowing to have like only A's or only B's. Let's say that I have 7 A's and 2 C's. So that means that I have balls 1 through 7 in box A. Box B is empty, and box C has 9 and 10. Right? Because, each of these spaces is labeled by a ball. So this one is D. And I don't want to count that if I'm saying, for my next cell in the table, I don't want empty boxes. So for this one over here, I don't want empty boxes. So this no longer works. I need to actually have strings of A, B's, and C's, but I need to use each letter at least once. I need to use each letter at least once. So let me go back to my table and let me just write here. Oops. So let me write here that this is actually strings of A's, B's, and C's, also length 10, but each letter is used, or yeah, all letters must be used.
Can you show the example again after?
Yeah. So let me go back here. So you see this one, this responds to this distribution. And this distribution is okay to be counted in both places. No empty boxes allowed or no empty boxes. This is okay to be counted in both. But this one over here that doesn't have these, it's okay to be counted on the left when empty boxes are allowed, but not on the right. In order to be counted in both, I need to have balls, at least one per box, no empty boxes, right? So I need to have at least one per box, which means that I need to have A's, B's, and C's. I need to have at least one A, at least one B, and at least one C. So remember that we saw the multinomial coefficient last time? We can think of this as, if you already know the number of A's, B's, and C's that you need, then you can use that multinomial coefficient. Let me just say this. I'm gonna introduce here a notation. These are called the T numbers. So, and then I'll tell you how to compute them and how it relates to the problem. So this is T of, actually, let me say, these are called the T numbers. And so in our case, is a T number 10, 3. Okay? And you can think of it as the strings of 3 letters of length 10 that use every single letter. All letters must be used. Okay? Or you can also say these are distributions of 10 different objects into 3 different boxes. Yeah? But you can think about it like this. And this is what we're going to try to solve. We have a formula for this one, but this formula we won't be able to prove until much later. So I'll give you the formula in a second, but I want to be able to write this in some way. And I want to convince you first that, this is the sum over all A, B, and C greater than or equal to 1, such that A plus B plus C is 10, of 10 choose A, B, C. So I'll convince you, I'll be able to explain to you why this is true. But I also want to use a formula that's easier to use. This is the sum from I equals 0 to, actually, let me do it like this. I can do this. 3 choose 10. Should I do it just for... No, let me write it in here so that we can generalize later. So I'm going to write the sum from I equals 0 to 3 of negative 1 to the I, 3 choose I, 3 minus I to the 10. Okay, now this one I won't be able to explain, and I will write the general one for M and N, any number of balls and boxes, but this one I will be able to explain. So let me try to explain this one. So I'm gonna go, so let me label these like that, so that you know that this goes with, this explanation goes with that one. So again, we're counting strings of A's, B's, and C's. I'm going to say here, number of strings of length 10 using A's, B's, and C's, where each letter must be used at least once. Okay, so the thing is that I don't know how to count that, but I do know how to do it if I specify how many A's, how many B's, and how many C's. For example, so I have many cases. Okay, so case 1, let's say 1A, 1A, 1B, 1A, 1B, and 8 C's. Yeah, so it's okay. I'm using each other. I want to count a number of strings using exactly 1A, 1B, and 8 C's. So the way that you do this is you have 10 spots in my word, and I'm choosing the 8 spots for the C's, right? So I choose the 8 spots for the C's, and then I choose from the remaining 2 spots, I choose 1 spot for the B. Or actually, you know what? Let me do it in order, since we have the A, B, and C. Sorry, guys. Let me just do A for B, for the A's, for the B's, and for the C's. So I choose 1 spot for the A, and from the remaining ones, I choose 1 spot for the B, and from the remaining ones, that's 8, I choose 8 spots for the C. This is the same as the multinomial coefficient that I showed you last time. This is just 10 divided by 1 factorial, 1 factorial, 8 factorial. 10 factorial divided by 1 factorial, 1 factorial, 8 factorial. Mm-hmm. So that's one case. But then I have many, many cases, right? I can have any number, maybe 1A, 2 B's, and 7 C's. So that will give me 10 choose 1 times 9 choose 2 times 7 choose 7. But, writing it like that is harder than just writing 10 choose 1, 2, 7, which is just the 10 factorial, 1 factorial, 1 factorial, 7 factorial, which you can actually see as just the rearrangements of these letters. I have 10 letters, I rearrange them, and because I have 7 C's, I need to divide by 7 factorial, or because I have 2 B's, I need to divide by 2 factorial. Well, the 1 factorial is not doing anything there, but yeah, so because I have 1A, I divide by 1 factorial. Yeah. So, but here the thing is that, I need to consider all of the cases, and I have many of them, right? So I cannot really, I could, but it's too many cases. I could also have, let's say, I could also have 1A, 7 B's, and 1A, 7 B's, and 2 C's. That's another possibility that will also give me that 10 choose 1, 7, 2, which is the same as the one that I wrote just above. But I will need to do these for, any possibility. I could have 3 A's, 2 B's, 5 C's. That will give me 10 choose 3, 2, 5, which is 10 factorial over 3 factorial, 2 factorial, 5 factorial. I will need to do that for every single possibility that gives me 10, for all this. There's at least 1 A, at least 1 B, and at least 1 C, all together being 10. There are lots of them. The notation that go ahead.
I just want to say, like, if we are looking at this, then we look at the 10 identical 10 identical balls with 3 identical boxes. So we will get like 8 unique answers from here. Because no matter how we
okay, yes. I see what you're saying, Cassie. Good. So you're looking at the partitions, right?
Yeah.
So these partitions, right? But here the order is important. So here it wasn't. So 118 was the same. Actually, 1 to 7. 1 to 7 was the same than 172, 271.
Yeah, I get that
whatever,
part,
right?
but I'm saying the unique answers, if we are going this way, then they would be 8.
Mm-hmm.
They might be repeating, but
yes, and then, yeah. So there will be 8 of these partitions, but for each partition you might have, for example, the 1 to 7
order.
is showing here, and the 1 to 7 is also showing here, right? And I need to count them as different here, whereas here it was just 1. But yes,
so maybe then we look at the permutations of that, and then
exactly. So it's gonna be more. But look. Let me write it first with with notation, and then we'll actually do it, right? Okay. So you keep going. You have all the possibilities, and this is one way to write it. We're gonna have 10 choose A, B, C, right? So that's like this, and we have all the different possibilities of A, B's, and C's. A, B, and C. All of them need to be greater than or equal to integers. So here everything is integer. And we need for the A plus C to be equal to 10. So that includes the 118, the 127, the 172. Those are counted as different. That's this. And because this is complicated, somebody said, okay, let's just give it a name. The name is, by definition, T103. Okay? So that's the name, so that you don't have to write this formula over and over. That's T103, is the T number 103. And this is the number of distributions. So this is the number of distributions. These are called distributions of 10 different objects. So the balls in our case, into 3 locations, the boxes. 3 different, I should say, this is important, 3 different locations. So these are the boxes that are different, and these are the objects that are different. No empty locations are allowed. Yeah. So that's the definition. That's the definition of this T103. Now, practically, how could you compute it? Right? So let's go to what Cassie was saying. We actually have the partitions. We know that there are 8 partitions. So I'm going to use those 8 partitions. I just know that I also need to consider the permutations of those partitions, the numerical partitions, the ones that I listed here. We have these 8 numerical partitions. The only thing is that we need to consider the permutations of the partitions. But there are different number of permutations for different partitions. For example, for the 118, there is less rearrangements than for the 127. But we can do this here, you see? So we can say, if we wanted to compute this precisely, this formula is going to have lots of terms. This has lots of terms, but we actually make it by grouping some of the terms into 8 groups. So, let me, because this is far away, let me bring this. Yeah. So I'm going to use those. And that's a relationship. So I'm going to use these to be able to write my sum. So I'm going to use the 118. So I'm going to use 10, 118. But in how many ways can I permute the 118? I can permute it in 3 factorial over 2 factorial because because I have 3, I have permutations or rearrangements, let me call them. Number of rearrangements. Oh, give me 1 sec. I'm going to do this. I'm going to write the partition. So that's a numerical partition. And then I'm going to write the number of rearrangements. So for the 118, when I'm looking at the number of rearrangements, I'm looking at 118, 181, and 811. Yeah. The number of rearrangements is actually, you have 3 objects and 2 of them are the same. So you divide by 2 factorial. So this is just. And so I need to multiply this times 3. But instead of just writing the 3, I'm going to write here the 3 factorial over 2 factorial, if you want, and 1 factorial. Right? So the factorial is for the 8 and the 2 factorial is for the 2 ones. The 3 is because I have 3 elements here. Yeah. And then I go to the next one, the 1 to 7. 1 plus 2 plus 7. And I want the number of rearrangements.
Why did you add 1 factorial?
Oh, that doesn't do anything, right?
Yeah,
just so that it looks. It's because there is an 8, and so when you take the rearrangements, you're supposed to divide by the number of repetitions of each letter factorial, and so you don't need to have the 1 here. You really don't. But just because we have 1 8, we have a 1 factorial. If we had 3 8s, we will have a 3 factorial. If we had 4 8s, we will have a 4 factorial, and so on. Mm-hmm.
Oh, okay. Mm-hmm. Thank you.
But yeah, I mean, if you don't want it, that it doesn't matter. And in fact, this is such a small number that we only have 2 types of partitions. We have the ones where you have 2 of the same and then another, like the 118 or the 334 or the 26. And then we have the ones like the 1 to 7 where all of them are different. And here we have 6. If I add them all, you're going to have 6, which is 3 factorial. Yeah. And so here we will write, here you will write 6 times, or maybe I should write it as 10 factorial. So, it's a partition 1 to 7, but it can appear in 3 factorial ways. And then I have the partition, the next one is 136. So 10, 1, 3, 6. And it can appear in 3 factorial ways. And then I have the next one, 1, 4, 5. So 10, 1, 4, 5. And it also can appear in 3 factorial ways. The next one is 2 to 6. So 10, 2 to 6. And that can appear in 3 factorial over 2 factorial ways, because there are 2 2's. So 3 ways. And then the next one is 2, 3, 5. So 10, 2, 3, 5. I'm just looking at these ones right here, right? The ones that we computed, the 8 that we computed earlier for numerical partitions. This is multiplied times 3 factorial. And then
I have a question, Professor.
Yes, go ahead.
Okay. I just want to tell you, like the line you are writing 3 factorial and 10 to 145. I just specifically I just want to know in this term how to tell in the word, only this term in the word, so that it would be clear to us how to set up the word problem.
Only this term?
Yeah, like a 3 factorial and then times 10 to 145. So in the word,
Yeah.
how can I tell these terms? Just tell this thing.
Okay, so the 145 is one of the many ways that you can write 10 as a sum of positive integers, right? So the
Yeah.
145 is because 1 plus 4 plus 5 is one way of writing 10, right?
Yeah.
So the 3 factorial comes from the fact that the number of ways that you can rearrange the 145. So you can have 154, all the different rearrangements. So let me write here. So you have the 145, the 154, 415, and so on, right? So 451 and so
like
on.
a six ways. It will be 6 ways.
It will be 6 ways. And that's the 3 factorial that we have here.
Right.
And the reason using that 3 factorial is because in this sum, in this sum, I'm supposed to consider all the ABCs in all the different orders that add up to 10. So here, this term is accounting for 6 of these terms. Is accounting for 10 choose 145, or 10 choose 154, also 10 choose 415, all of these triples. So this is accounted by 6 of this, all the ones that use 1, 4, and 5 in some order. Make sense?
But my question is, like, when we are multiplied by 3 factorial for the word base in the word problem, what things to look at the word, why we have to use 3 factorial times this?
Because you see, this one, it's actually accounting for, is another way to write 10 choose 145 plus 10 choose 154 plus 10 choose 451.
Right.
415 plus 10 choose 514 and choose 541. So instead of writing all of this, I write one of them. It doesn't have to be 145. I can use this one because all of these are equal. All of this, you see, all of these, each is equal to 10 factorial over 1 factorial, 4 factorial, 5 factorial, in some order, the product on the bottom, right? So all of them are equal. And therefore, I can just say, how many do we have? And then multiply by one of them times one of them. So I can choose any one of these. I decided to use the 145, but I could choose any one of these and then multiply by how many. And how do I know how many? I just need to count how many ways I can write the 145 in different orders. And that happens to be 3 factorial. That's why I have the 3 factorial.
Okay.
Make sense?
Okay.
And so that's what I'm doing for all of them. Yeah. So that's what I'm doing for all of them. I'm just grouping them. This one is accounting by the 10 choose 136, 163, 316, all of them. And this is only a 3, because this one is only accounting, this one, it's 3 times, right? The 3 factorial over 2 factorial is only 3.
Is it 3 times?
That one is accounting. It's just 3 times, right? Because I only have the 10,118 plus the 10,181 plus the 10,811. That's why it's only 3. But the way that I can count the rearrangements of 118 is 3 factorial, because I have 3 symbols, but 2 of them are the same. So I divide by 2 factorial. And I'm missing one more here. 1, 2, 3. I need to have 8. The last partition is 10,334. And that one is also 3 factorial. 3 factorial over 2 factorial. So that's what this is.
Mm.
And so if you actually do all of this, I did it before. It gives you 55,980. Mm-hmm. But that's so. In other words, the T number, the T103, is this one over here. Always, all right. Now the thing is that we want to be able to use the T numbers for any N and M. So we're going to talk more about that next time. Mm-hmm. But for now, let's just stick to this example. And so, there's a big explanation for that T number that, again, let me go back to my table. This, there is another way that you can compute it. I'll tell you more about it next time, but we won't be able to prove it until after the exam. We're going to see the principle of inclusion-exclusion and, this other way to write it, which is the easiest way to compute it. It's we're not going to see until much later. But anyways, you have it in that table. This happens to be that. And, just go with the T108 as we, we'll learn more about how to compute these T numbers. But in general, they're harder. Although, here's a formula that you can use. Mm-hmm. Okay, in the last 2 minutes, but then I won't explain. We'll explain them next time, but I'm just going to write what goes here. These are called the Stirling numbers of the second kind. That's the name. There is some history here. But so this one is different objects into identical boxes. This is denoted by S103. And the formula is actually the T number divided by, that second number factorial. I will write this for M and N in general next time, but that's what this is: the T number divided by that second number factorial. Mm-hmm. It has to be with the number of ways that you can permute the three boxes, but we'll explain it next time. So this one happens to be, we already had the value of the T number. So this happens to be 9,330, but just remember that that's the S103. And therefore, once you have that, this is not allowing empty boxes. If you do allow empty boxes, then it's going to be like for the partitions. This is just going to be S103 plus S102, no empty boxes, one empty box, or two empty boxes. Mm-hmm. And so this happens to be T103 over 3 factorial plus T102, which we didn't compute, but we could, and T101 over 1 factorial. And so that this happens to be 9,842. So a little bit more than this. But you could use the formula. We could use this for. Yes, go ahead.
Oh, what's the difference between S and T?
S is T divided by a factorial. And the difference in terms of what they mean is that here you have distributions, for the T numbers, is distributions into different boxes. And for the S numbers is into identical boxes. In both of them, the balls are different, the objects are different, but the boxes are different there, identical here. So the S numbers are smaller, and they happen to be smaller by a factor of, in this case, 3 factorial. Okay? But I'll explain a little bit more about, the context and how to compute these things. But at least you have like a full table of the 8 different cases. We'll do the next class activity, which is already there on Tuesday. So please bring it. It's balls and boxes activity. We'll go over that one. All the problems that I selected from section C and D that I are already assigned are on this. of course, variations of this, but it's a variation of these 8 problems.
Professor,
Okay?
I have a question. We have to
Yes.
do our Wiki in this week or the coming week? C and D.
Oh, C and D is due in a week from today.
From today?
So you have until from today. Yeah. So take a look at your problem. See if you can solve it. See if you have questions. We just got started, right? But get familiar with your problem so that if you recognize something next time, or if you have questions, you can always ask, right? But all of the problems that I assigned today, one way or another, fit into this table. Maybe different parts of the table, but it's all of them are these ideas. This is all we're gonna do.
Like C and D will be a 2 days lecture, based on two days lecture.
Oh, for your problem.
Yeah,
Yeah.
It will be based
Yeah, we
on
still
2 days
have-
lecture.
Yeah. We still have next week.
Okay,
But take a look at your problems. Okay, guys, I know time's up, so if you need to leave, please feel free. But I'm here if there are more questions.
Okay, thank you, Professor. Thank you very much.
No problem. Take a look at your
Professor.
problems, make sure some of them, many of you will already be able to solve your problem. Like they really just fit this table, some of them. And by the way, I went in reverse order on the table because, at the beginning, the beginning problems for section A were easier. And then the last problems for section B were harder. So I thought it was better to go backwards this time. So people who got the hardest problems from section B are getting the easier problems from section C. So I just assigned them backwards all at the same time. So hopefully that will balance things out. But again, if it happens to be a really, really impossible problem for you, you can always pass. But before doing that, ask me questions and wait a little bit because we just got started with this.
I had a quick question for you. Are you going to go over probability, or are we kind of on our own for that?
You're kind of on your own, but not really. You can ask me. But let's say the only thing that you really need is to understand that it's always favorable cases over total number of cases. So these probability problems should really be about counting, not about probability, So it really is count 2 things: count the total number of cases and count the favorable cases. That's it. So in that sense, if you have any questions about if you got a probability problem, just let me know and I can tell you, yes, count this and count that and divide them. So it is a counting problem. It should be.
Yeah, because mine split into 2 parts. It was the first part was like the counting part, and then the second part was the probability part. So.
Okay, which problem is it, Scott? Do you have a little bit of time?
It was 44 and 45, and I had
in section B.
From that, yeah.
Oh, okay. So you have 3 parts of 44 and 3 parts of 45.
Yeah,
right?
and I feel like I'm on the right track, just kind of splitting it up with the suits and the cards and the, total 52 and all that. So, all right. I can dig in on that.
Okay. So, yeah. No, so as long as you're able to do 44, which is the counting one, for 45, it's just going to be divide whatever you got in 44, divide by, so you're selecting 5 cards, right? So divide by, depending on how you are, it's going to be either 50 to choose 5 if you're using combinations for the rest.
Okay.
Or it's going to be 52 times, whatever you got over 52 times 51 times 50 times 49 times 48.
Hi, Professor.
Yeah, I got
Thanks. Bye-bye.
Is it okay I try to come to your office hours to try and figure out the team numbers?
Yeah.
Thing? I was kind of a little lost.
Yeah, no problem. Just come over.
Okay, it'll have
copy.
to be at 1:45 today because that's when my Math 442A class said.
That's fine. Bye, Sean. So, Scott, yeah. So as soon as you have your answers for 544, it's just going to be a matter of deciding, depending on how you counted them, it's going to be either a binomial or a product of 5, 54, 51, 50.
Over binomial, just all that.
Yeah,
crazy.
whatever you go from part 44,
Okay.
divided most likely, because most likely you are using combinations for the first one, but I'm not sure.
Yeah,
Most
yeah.
likely it's just going to be divided by 50 to choose 5. So there is not real, you don't need to know much about probability, just favorable over total number of pieces.
Okay. Thank you.
But ask me. You can always, quick
Yeah.
email and I'll let you know. Okay?
Yeah.
All right.
Well, thank you.
Okay. Okay,
Professor.
bye-bye.
Professor.
I have a question. Oh, sorry.
Yeah.
For the midterm exam, is it going to be take home or in-class quiz?
No, it's during the class time. All the instructions are in the syllabus. If you want to take a look, and then you can ask me whatever you need. But yeah, it's during class. Take a look at the syllabus, and you'll see. Yeah.
Thank you.